quickly go through the last problem of these three. This is on the homework for math analysis, where we're just starting to look at instantaneous rate of change. We've done limits, and we're going to use limits to find the instantaneous rate of change to this function at x equals -2. So in class, we set it up in a little more detail than we're going to use right now. We drew a graph. Maybe we'll do that at the end. We used the calculator with table to kind of approximate the limit. But here, we're just going to set it up. And so again, our slope formula that we're using, the one we used in class, was the kind of traditional slope formula we're most used to. F of b minus f of a over b minus a, right? Just the slope of a line through 2 points. And what we're doing is, for b, we're using the variable x. And for a, we're using this value here, the x coordinate of the point of tangency that we want, like where that tangent line will be. So we're going to set that up over here. And we're going to leave a little room here because it's going to be a limit. We'll talk about that part in a second, but I'm leaving room for the limit. And what I want here is, I'll just use f for now, f of x minus f of -2 over x minus -2. Okay, that's my slope formula. So again, this is the slope of a secant line, right? If I have a curve, a secant line is a line through 2 points on the curve. And the idea is that we have a point x, and we have a point at x equals -2. We're just calling this x coordinate x. And we're taking y2 minus y1, so this change in y, over x2 minus x1, the change in x, and that gives us the slope of the line. And that's called the slope of a secant line, right? But what we want is the slope of the tangent line at x. And so what we're going to do is take that point there, and we're going to bring it closer and closer and closer to x, because every time that point gets closer to x, our slope of our secant line gets closer to the slope of the tangent line that we want. Okay, that's the idea. So we have to set up that limit. So, I was wondering if I was going to do that. All right, let me rewrite that really quick. F of x minus f of -2 over x minus -2. Again, what we're doing is taking the limit, though, because we want that second point that I just showed to approach the point of tangency at -2. So we're going to take the limit as x approaches -2. That's the setup. Okay? So we're going to rewrite this now. The limit as x approaches -2. And on the bottom, we have x minus -2. That's x plus 2. Keep it simple, right? Obviously, that's going to be 0 if we plug in -2 for x, if we do direct substitution. We're expecting 0 over 0. When you do a derivative, it's always going to start out as 0 over 0 with direct substitution. So what we want to do now is use this for f of x, 3 over 2x plus 1. And then we need f of -2 to plug in here, right, for this. And so if we find that, here, f of -2 is, with this f, right, 3 over 2 times -2 is -4 plus 1. So that's -3. 3 over -3 is -1. Okay. And here, if you were to plug in -2 on the bottom, we're going to get that -1. And so we'll have -1 minus -1 on top, which is 0. So we are getting 0 over 0 through direct substitution. That's that indeterminate form. That means we have more work to do, right? It doesn't mean the limit does not exist. It means, well, we have to get rid of the factor that's giving us 0 over 0, which is this factor right here. And so if you look at your flow chart, or if you just maybe we need to do some algebra, because in here is a hidden factor of x plus 2. We have to pull it out. And to flush out that factor of x plus 2, we're just going to do a little algebra. We're going to multiply the top and bottom by the lowest common denominator of any little fractions in our fraction, because what we have here is a complex fraction. So if we clear the little fractions, if we clear the little denominators, we should be able to find our x plus 2 factor on top. So multiply by that LCD. When we distribute to there, they just cancel out. The 2x plus 1 and 2x plus 1 cancels out, and we just get 3. And then when we distribute to here, we're going to keep that part on top. So again, we're going to get 3 when we distribute to the first term. And then we had minus -1, so let's just make it plus 1. And that's times 2x plus 1. So plus 2x plus 1. It's 1 times 2x plus 1, right? And on the bottom, and that was nice and simple. On the bottom, we don't want to distribute. Do not distribute this, again, because we want to cancel the x plus 2. So we leave it factored. And there should be, here, let me rewrite the limit now. If we did it right, if things are working, there should be an x plus 2 factor in here. And there is. That's 2x plus 4, which factors to 2x plus 2. On the bottom, we just have x plus 2 times 2x plus 1. Again, it's the limit as x approaches -2 of this. We haven't gotten rid of the limit yet because we haven't evaluated it. So now, in order to do that, we're going to cancel the offending factor. The x plus 2 is what's giving us the 0 over 0. Now we can plug in the -2 to what's left. And on the bottom, we get -3, right? Because -4 plus 1. And when you do that, when you're able to plug in that -2 and get an answer, right? Like not a 0 over 0, but an actual value, that means that you're done. You can drop the limit now because you've evaluated it. When your direct substitution gives you a nice answer, you are evaluating the limit. That's the slope of the tangent line. M equals -2/3. And so my tangent line is, if I want to write the equation, I'm going to use point slope form. Y minus y1 equals m times x minus x1. So let's go ahead and do that. Y minus y1. Our y1 was this -1, right? That was like f of -2. So y minus -1, y plus 1 equals -2/3 times x minus x1, which is the -2. So x plus 2. That's my tangent line equation. Okay. And if I wanted to, I could go and I could graph in my calculator y1, and then I could graph the tangent line as y2. I'd have to add the -1 over to the other side. And you'll see that it is, in fact, a nice tangent line.